Dr. Gerhard Klimeck received his electrical engineering degree in 1990 from Ruhr University in Bochum, Germany, and his research was concerned with the study of laser noise propagation. In 1994, he received his PhD from Purdue University, where he studied electron transport through quantum dots, resonant tunneling diodes, and 2D electron gases. Dr. Klimeck then became a member of the technical staff at the Central Research Lab at Texas Instruments. And in 1998, he joined the NASA JPL, joined the JPL Jet Propulsion Laboratory as a senior member of technical staff. In 2002, he became a principal member of JPL. In December 2003, he returned back to Purdue University, where he is now a professor of electrical and computer engineering. Since May 2009, Dr. Klimeck also serves as the director of the Electrical and Computer of the National Science Foundation Network for Computational Nanotechnology, NCN, which he led early on as a technical director. Dr. Klimeck's work is documented in over 250 peer-reviewed publications and over 400 conference presentations, over 100 invited seminars, and more than 70 technical reviews. He's also a fellow of IEEE. And with that, please join me in welcoming Professor Klimeck to deliver his speech.
Thank you very much for having me today. I like to lead off my presentations on nanoHUB with this interactive map. This is a visualization of real data taken about a year ago. And what you see here is obviously a day-night animation over a week in February of last year. You see a lot of blinking objects. The size of the object reflects the number of people that arrive at that particular time slot at that particular location. You see some green bars. Those are people signing up for nanoHUB. They turn into yellow dots. Those are then people that run simulations. We have about year over year 12,000 people that run simulations without installing any software and utilizing it. And I'll talk about what they might utilize it for. You see a whole lot more red dots. Those are people that look at lectures, seminars, and tutorials. And you don't have to sign up for it. It's completely open. And you sort of see a burst-like behavior. So there's a lot of people arriving from the same location, and you start to wonder what they might be doing. And I'll talk a little bit about that as well. So you've seen the lengthy title. A shorter version of that might be just nanoHUB. And you've seen the blinking lights. Now I'm showing you a more static version. These are the people that showed up last year on nanoHUB, overlaid with a famous NASA World at Night picture. So basically you could argue we keep people up at night because wherever there's light on pretty much civilization, we have nanoHUB users, which is, to me, a pretty impressive thing. What I also talk about is really that there's knowledge transfer happening through this mechanism, and I want to highlight some of the requirements for this knowledge transfer. And I'm talking a lot about all the things we were told we couldn't do over the last 10 years since we created nanoHUB and made it work. So I give it another headline, myth-busting. Talk about all the things we were told we couldn't do and how we had to get around these myths that seem to exist. We've seen significant growth in the number of users, simulation users. We were sort of flat, about 1,000 users, and suddenly we changed something. And what we changed is we went from web forms that you might know what your bank has, which are pretty boring, right? You fill out some numbers, you hit a query, and you get an image or some data you can't really do anything with. We turned that into an interactive application, and suddenly we see a little bit of growth. We introduced, so we started this project here actually formally in February of 2002. We knew we needed some time to put in place a new system, so we had a decoy in a sense on, well, we got to do something in the meantime. Let's put some lectures on nanoHUB about nanotechnology, etc. And our decoy took off quite a bit more. In fact, it's 20 times more users that look at lectures and tutorials compared to the simulation users. So that turned out very well. There's a lot of talk about MOOCs these days that are online education units. I think we have effectively over the last few years had a MOOC type environment where we are close to 250,000 users. Actually, we're like 100 users short of 250,000 right now. And we had our own stock market crash right here. We started to wonder what happened, so I can tell you about that as well. I need to start these lectures with a usual showing of the research groups, right? So this is my research group. It's about 30 people where we study nanoelectronics and electron flow, so they contribute a lot to nanoHUB. I also lead a team of professionals. They're much more excitable than these guys. So this group over here is really in charge of nanoHUB as such, the operation, the upgrades, the technology under the hood. And this group, research group, is one of many that contribute. In fact, we have over 1,000 people that contributed content to nanoHUB. And without all of these contributors, we couldn't show any of these results. So things really go to a community that is now coming to nanoHUB to contribute and making it work. So I'm going to start out, because I'm assuming most of you have not been on nanoHUB, with a sort of a brief video that summarizes nanoHUB.
Imagine a technology that helps you explore a new area of science. And not only download resources, but learn from leading researchers online. Not with blurry videos, but through animated seminars where you can hear the speaker talk and clearly see his slides. Where you can search for concepts and get right to the point. Imagine having fingertip access to simulation tools that are easy to launch. Tools with intuitive controls that are well documented. And results that are readily visualized. And not just one tool, but dozens of tools that simulate many different phenomena.
This is a biological pore where ions flow through. This is a device we worked at TI called resonant tunneling diode. This is a quantum dot where you can make an artificial atom and have s and p orbitals, a structure that consists of millions of atoms.
Tools that are not just Java applets, but real research codes that are connected to national grid resources. If you have questions about the results or the underlying models, imagine being able to ask experts throughout the world.
We actually have a virtual economy where you can earn nanos and spend nanos on nanoHUB. It's a sort of a rapid overview, and you know, computing in the traditional way, if you do computing on a high-performance computer, you have to apply for a grant, you have to be kind of being in the in-crowd, and it's kind of unusual that you actually get something for free. So this is actually a really free site, really, we don't ask for your credit card, and still, even if I show this, usually when I give a talk, later somebody will come to me and say, hey, can you help me sign up? Like, no, you just go there and it's free, right? You sign up just like for a Gmail account or a Yahoo account. You have to give us a little bit of your name and an email address, but that's it. So you don't have to be in the in-crowd, you don't have to know the PI on the program, you can go there and use it. But let's go back to sort of the origin of why we thought this might actually work. and then sort of think about the various barriers we had to break through later. So 1965 is a very, very important year. Maybe not to you, but to me. I was born. So, but for many other reasons, somebody else sketched something into his notebook. And that person sketched the number of components per integrated circuit versus the relative manufacturing cost per component. So this is an economic law written down by Gordon Moore, who was a co-founder of a company we call Intel, one of the small companies we have in the US. So this is Moore's law. It was an economic law that allowed to produce more chips, more powerful chips as you continue to develop them by downscaling them. You might have seen Moore's law in this kind of plot, if you ever seen it. These are the number of years of development, so from 1970 to today. So today, we are at the stage where we have 2 billion transistors on a chip that is not bigger than your thumbnail. So that's, to put that in perspective, that's a third of the world population of all human beings working together in some cohesive form, not having war, and actually doing a task together. That's quite a technology achievement. So that's device integration. Another form of Moore's law is this one, where we plot how devices are getting smaller and smaller from traditional transistors up here to devices that look three-dimensional. And I love to show this old chart from 2004 because we are now at 2013, and in 2011 and 12, Intel indeed did announce their 222 nanometer node. So they knew 6 years, 7 years ahead of time where they will be. They have a road mapping, right? Today, it's not so clear where they're going to be in 10 years. Okay, so we are at the end of this roadmap. We're approaching the end of the roadmap. So, but that's not the point of this presentation. The point here that I want to make is that there's two pieces of software that enabled these processes. One was, how do you simulate and understand how 2 billion things work together? You have to have a circuit type tool that analyzes that. That's away from the devices, but really puts functionality in circuit integration. And that tool is called SPICE. And the way to make things smaller is done by process simulation, where you really understand what happens if I etched this semiconductor, what if I implant it with impurities, etc. So it's really a process control simulation, a process management software. And that's SUPREM. So if you're an electrical engineer, you'd say, of course, I know that, right? I presume you're not. But what most electrical engineers really don't know anymore either is where these pieces of software come from. You might say, well, it says so, Stanford and Berkeley. No, I mean where they really come from. Berkeley SPICE started as a teaching tool between a single professor and a single student. And it was created to study circuits. And from then on, it evolved into something much bigger that is now an industry standard that is available, and you can buy a copy for $100,000 from a variety of vendors if you're in the industry, or you can get a student version for $100 or so. But it's the industry standard, but it came out of basically a teaching moment. And Peterson, this professor here, made this a first open source code, one of the first open source code, and he carried it around on tapes. This is pre-internet, and said, okay, here's a piece of research code. It probably has bugs in it, but try it anyhow and let me know when it doesn't work, because then I can make it better. The point is, software will always have bugs. There is no such thing as a perfect piece of software. That means quality control goes with that person's name. Okay? So if that person is dedicated to making it better, that's what you want to achieve as you migrate through evolutions of pieces of software. That's the dedication you need. Stanford got wind of the Berkeley success and said we have to kind of do the same, but they did it now for process modeling in the same form. And also there, students that would graduate take it along to industry, or that they would take it along to academia, and it would propagate through there into a variety of things. That's a point I will try to highlight again at the end of my presentation. So really, from process simulation and circuit simulation, we have a birth of a whole new industry that is today at about $300 billion. This is the largest US export industry. You may not be aware of it, but semiconductor chips are the largest US exports. All right, so now the idea is, could you do something like that in the future with a whole bunch of research in nano for upscaling to billions of nanostructures and downscale to nanoscale structures, and in a variety of areas, in electronics, materials, photonics, mechanics, biomedicine, and put them in the real world. So that's the goal of NCN and nanoHUB that I represent as an organization, and to make this happen. So that's a nice goal, but what does that mean? And what are the hurdles that you want to overcome? I presume you might think, when you think nanotechnology, you might think people in bunny suits, right? And sort of small chips that are fragile. You might think of an expensive facility like this, what we have at Purdue, costs a mere $60 million to build just a building, not even to put stuff into it, right? So that sounds pretty expensive. So there's a whole world of experimental work out there. You might also think of nanotechnology in terms of carbon nanotubes. So here's a visualization of 3 different nanotubes. And by the way, anybody in the world can now make this visualization. That is what I mean by an interactive tool, where you can actually compare things and visualize them, rather than sort of an Excel data sheet that you have to download and do something else with, right? That's what I mean by an interactive visualization. Here's a quantum dot that was already shown in the video. These are artificial atoms, and this is an animation or visualization anybody in the world can now do. So these are computational models in a sense, right? They're not, in that sense, real, right? These things live on a computer system, like something like that on racks, and they're operated by people like me, geeks like me that like to write software and understand these things. What you might also appreciate is that there's typically a pretty big barrier in between these guys here and us over here. We have our computational models, sometimes we work together, but often there's a huge barrier in between, and you ask yourself, wouldn't it be cool if you could actually bridge that barrier? If these guys here, those experimentalists, could actually utilize some of these models to maybe help their experiments. That would mean, at the first place, we would have to make our stuff available. Maybe it should be lots of us making it available, so these things are vetted and controlled, and there's some quality metrics to it, and we believe that they work, and then maybe a lot of these guys would also show up and use it. But these are not the only barriers that are out there. But you might even want to dream about using this in the classroom and use it for education and for teaching. Or maybe, just maybe, you want to have economic impact and also have that be used in industry. And of course, all of that has to happen without really installing any software. It should be easy to use, should run in any browser. Now, this is in a sense sort of a common dream of breaking the barriers, right? If you just take away nano out of this picture and replace it with any field of science or engineering, you end up with quite a common dream of really breaking down barriers between different roles of people in the way they interact, education and industrial impact. And lots of people have written proposals on how to do that. And it's kind of hard to actually achieve it. And you might want to ask yourself, why is this so hard? And I would argue we've solved some of these problems, and part of that has to do with how we look at this overall interaction that we're trying to have here. In a sense, you can think of us computing geeks here in that sense. We're suppliers, and we have products. And the products ultimately need to serve some customers, and you've got to put it in the marketplace that then holds these products. And there's a lot of people that talk about e-science. And e-science is typically worried about the market. We'll create a market. But they typically don't even talk to the customers or the suppliers. They create a market that I can't contribute to. There's a lot of the little science gateways out there that are focused on the suppliers. Well, I have something cool, I just want to share it. But they don't worry about how to share it or how the customers would like to receive this material or how they would utilize it. And in that sense, there's a lot of trials to do that, but they typically omit looking at all three components: the marketplace itself, the products, the customers, and the suppliers. And only if you are able to meet the requirements of all of these components can you really make this work. Since I'm a supplier, I'm going to worry first about how can we get things into a market? What's the process of making this work? So first of all, to provide this in the internet, this is typically not what we do. In fact, you can argue that most scientific codes and research codes are written by one person for one person. In principle, most graduate advisors at a research university can barely operate the software that their students wrote. Right? So there's really just one person in the world that can generate this. This calls into question whether this stuff is duplicatable. Right? There's some issues with that. But really, in general, we don't do this. And maybe if you have a piece of code that looks like this is actually incredibly structured and well documentable. It's complete gobbledygook to you, right? But this is actually, in my group, that would be a good input deck if you specialize and know what you're talking about. But overall, I would call that user hostile, right? You want to get from user hostile to something like this that a undergraduate student could operate, where they want to maybe simulate a quantum dot that has a certain shape and a certain size, certain masses or material properties. And this is a graphical representation of the same gobbledygook that you couldn't understand anything. Okay? But basically, it's a one-to-one correspondence. One is usable, the other is not. So you want to get to user-friendly and really think about the customers that could actually use that. Right? And the customer is not people like me or my graduate students, it's people that are different than us. All right, so you got to have some technology for doing that. And the other thing you have to do is you got to give my students and me to put that on the web. So that's another story where you have to have technology that is also then developer friendly or supplier friendly. And we've built this technology with what we call Rapture. I'm not going to talk about it. And we have Hub 0, which is the baseline for nanoHUB, that builds this market to make it all accessible. Right? So that's, again, these three components you have to put together. And since this has been so hard, people have sort of developed some myths around it, why this might be very hard. And these myths are, on the user side, sort of the customer side, people actually have told me throughout the years, you can't use somebody else's code and conduct research. You have to write your own code to do research. You have to know every single line of code in there to conduct research. And certainly you can't use it for education either, right? It has to be a special piece of code that can be used for education. Now, last time you rented a car at the airport, did you really read the 200-page manual and disassemble the engine and then reassembled it before you drove off? I don't think so. How many documentations did you read about your iPhone apps? Any show of hands? Okay, thank you. So the point is, you can make it easy for people to use something if you standardize it to a certain degree and actually make it accessible. So the question is, we still have to prove that it can be done, and can you generate some data? On the developer side, it is perceived that building user interfaces that are actually user-friendly is very, very hard. It takes a lot of time, and I just want to graduate and get my PhD, right? And why should I share my code? Because that's my special advantage, right? I can write papers myself, thank you very much. So where's the incentive to share? And by the way, typically in all other web development environments, I know you have to rewrite your code to put it on the web. Why would I do that? I don't have time for that. So there's, on the developer side, there's some myths. And then, of course, there was no end-to-end science cloud until we actually had nanoHUB. So there was no accessibility that puts it together. All right, so I'm going to pick up a little bit here again. So customers, markets, suppliers. Now, I'm going to start with these developer issues. because that's my perspective, that's how we sort of entered. And the most proposals that I know and most science gateways that I am aware of, or science portals, whatever you want to call them, their proposals read like this. We got a really cool piece of code. I'm a researcher. We want to put that on the web. All right, so now we write a proposal where we're going to hire a web developer. And that web developer will take that code and put it on the web. These two speak a different language. This person is Java, PHP, Perl. This guy is C, C++, MATLAB, Fortran, something else. Certainly not web languages. There's a lot of transfer from one to the other. Now, it takes about 2 to 3 years in this process to rewrite a piece of code. Now, which researcher do you know sits on their butt for 2 to 3 years and doesn't modify their code? All right? I don't know any. Right? So in 2 or 3 years, this guy is starting to develop new pieces of code. Gets pretty aggravated because that code over here has nothing to do with it anymore, right? He has a new version of code every other week. Meanwhile, it takes this guy 2 or 3 years to put something up. And this person here will never touch this because he knows, she knows, it's already outdated. Why would I touch something old? Right? So it takes about, in a typical proposal, about 500K per tool. And by the way, no new research has been done. So this guy here that's interested in research gets really aggravated. And just to elevate the numbers a little bit, if you wanted to put up 175 tools in 4 years, it'll take you $88 million. And I can guarantee you that NSF will not give us that kind of money. So this is not a model that is really scalable. And since it's not scalable, it's really sort of shining light on the fact that you could call these guys suppliers and you have a subcontractor or a consultant that we're not really happy with. So in this process, what happens to customers really develop a different feeling for, well, this can't be real research out there, right? These might be toy applications, certainly not deep research, and maybe, just maybe, I can use that for education. So they really scale back the expectation, and that overall develops a pretty bad reputation in this whole circle of science gateways and portals. And that's where a lot of these myths come from, because this process over here is really broken. Now, how do you fix that? Well, we think we fixed it. In nanoHUB, we have created 175 tools in 4 years without the $88 million. We basically eliminate this bottleneck. We enable researchers to put up their own codes in about 1 to 2 weeks. And that makes this guy much happier, and he can develop, or she can develop, a variety of softwares, and I'd like to show next that this actually works. Oh, in this slide, sorry. The way we make this work is we give researchers a development workspace that is something that runs in their browser that mimics what it's ultimately going to look like on nanoHUB. We give them software repositories, software mechanisms. We give them a way to connect to grid computing that's transparent. We give them a staging and testing environment and a way to then publish their codes. And all of that is sort of almost like an inverse shopping process. Just like when you go shopping on Amazon, you give them a credit card, you get something. We have the reverse where somebody contributes pieces of software and we walk them through a web-based process. And I'll show some of the highlights of that later. But you can think of this as your new or modern machine shop that really engages a lot of people, that gives them tools at their hands that then allows them to reach markets. And in this slide, I want to show you that this really works. And what I'm showing you here is, in blue, are the number of tools that come online. So we are now at 260. That's a little bit over a year old now. We have over 300 developers that's shown in green. And these developers create new versions, as I said, right? They're researchers. There's now over 1,400 versions of codes available. And you can call this the number of suppliers, the products, and the product innovation that you really enable. And it's no longer just a static piece of code that sits on somebody's website and somebody else has to download it. These are live scientific objects that get updated all the time. The way that it's done is sort of what I meant by this infrastructure, the web-based infrastructure where we can connect tool developers to end users. And that's sort of a staged process where a tool gets registered, then created, uploaded, installed, and approved and published. And you can think of that again as connecting customers to suppliers through a web-based publishing system. So there's no more emails flying back and forth between the developer and the core person that sits here on the infrastructure side, but it's regulated in a sense in a well-defined process flow that is scalable. And I want to show you that it's scalable. So here's a representation of these tools, right? So each dot is a tool on nanoHUB as of January of 2009, so it's already 4 years old. All these tools have different statuses, right? So they are published or approved or installed or registered. And you'll see more and more appear here, and you'll see little lines shooting across if and when there needs to be a connectivity to the central site that sort of says, okay, I need to install it or I need to publish it. That is where we take action. The rest is all taken by the developers. And when the developers take action, these things wiggle a little bit. So you sort of see tools coming online. They go through certain stages. So these blue ones are now approved. Eventually they get published. And you basically see most of the action happening on the perimeter, not necessarily to the central node, which means this is scalable. We don't have to interact with every single action a software developer takes. They do most of the work, and we do a little bit of action later. So this goes through the year, starting in January. So in the summer, it gets a little slower. Then when the beginning of the semester in August starts, it gets a little bit more hectic because somebody says, okay, I want to use this tool in my class, right? I did some fixes. Now I want to get it done. So then it slows down throughout the semester a little bit. Then things happen in terms of updates. Then the semester starts to wind down, right? Now it's starting to be Christmassy. Right? So silent night over here, and then the semester starts again. So the point is it goes through a sort of a life cycle, and believe it or not, this is managed by one person on the central site, interacting with 400 developers. Not one project, one software guy, 300 projects, 400 developers, one software guy. That is a scalable solution on why we can reach a lot of tools. Now, I mentioned a lot of the work is being done by these software developers. You can call them suppliers. So each dot is now a tool, and the linkages between these dots are the common authors on these tools. So you see basically the suppliers form a network around their products. And the yellow dots come from Purdue, the orange ones come from from Illinois. Here's Northwestern. This is University of Florida early on. Stanford was sort of isolated, and they eventually left the network. The white dots are really cool, and those are people that come from the outside in general. So those are tools that are being contributed that are not formally affiliated with us. So you see actually the suppliers build networks, which is kind of interesting. So the supply chain seems to work, but now the question remains, what are the market incentives for these suppliers? Why should they contribute, right? So let me highlight some of those. So here I'm showing you a different chart where each dot is a supplier, or call them software developer. And they're charted as a function of number of collaborators they have on this axis versus the number of users they serve. So the essence of the message is if you have a lot of collaborators, you can reach a lot of users. So collaboration is a good thing. Well, here's real data. I'm not making it up, right? This is quantitative data. You can think of that as your supplier network. If your supplier network is extensive, you can reach a lot of customers. But that is not maybe a whole lot of incentive yet. So here's another example. This is Dragica Veseleska. I work with her quite closely. She's a prof at Arizona State. She was one of the very early contributors to nanoHUB. She has put up some 17 tools on nanoHUB, served 11,000 users. That's a whole lot better than the few people that read papers, right? So it's a different number. These kind of charts we give to every contributor. So when they write a proposal to NSF and say, I have an outreach program, my research output reads real people, this is not possibly maybe eventually, no, this is hard data, right? And then sort of a little bit of advertisement, we just wrote a book with her on computational electronics that embraces these tools that are nanoHUB, so we start writing books around these tools as well. Here's a younger person, he's a former postdoc in my group of students. In his time, he published some 8 tools, served some 6,000 users over the years, and eventually he became a faculty member at Southern Illinois, and there was no activity in terms of nanoHUB at Southern Illinois until he about arrives, and some of the activities show up from that side. And he integrated nanoHUB into his existing classes. He built a new curriculum and used it for research. Remember when I said SPICE and SUPREM started to migrate away from the origin and went into other sites? So this is an example of that. And the reward he got was he was promoted with tenure after 2 years versus 5. That's not bad. So it starts to form incentive systems for people to integrate and to innovate. All right, so we are on iTunes U for a couple of years now. It was kind of hard to get in. We had to talk to Apple executives, and the right one actually called us later a nano app store, which is kind of an interesting way of looking at it. So they consider us like a university. We really leverage new markets that way. We started to put our animations and visualizations into Wikipedia and make Wikipedia better. And I thought, well, I have a pretty diverse group. Maybe I should have these things translated from English to other languages. But it turned out within 2 weeks or so, these things get translated into other sites. And of course, Germans know what a buckyball really looks like. So the point is we're starting to drive real users now from Wikipedia into nanoHUB when they want to find more. So it's again, think of it as a different advertisement by helping other sites and really driving traffic. So I would say with 260 tools being online, this is the quantitative proof. It's not too hard to put these tools online. And we've built incentive systems, and you don't have to rewrite your code. I haven't told you how it's being done and all that, but let's just state you don't need to do it. So these myths are somewhat busted. But let me pick up these other ones here for a second. So I think in terms of accessibility or market, this picture speaks 1,000 words. Apparently we're accessible all over the world. I think our downtime throughout the whole year last year was some 30 hours in total. So this is a 24/7 operation. It doesn't run out of the corner of my lab or so. There's a whole infrastructure group working on this. So there's a market. Apparently there's a lot of customers. But remember, you can't do research on this, right? You have to write your own code to do research. And certainly you can't use it for education. But still, you start to wonder about what all these people are doing. So let's pick up on that and see what they're doing. One way to think of this is we've created our own matrix. Right? We have a big computer system where not everybody tells us what they're doing. And it's kind of too hard to survey them all on what they're doing. So we began to run analysis tools on these usage patterns. So let me explain to you how we do that. So imagine a user coming to the site, and on one day they run the green tool, then they don't come back, and then the third day they run the orange tool, and then again the green tool. So in a sequence of days, you might see some specks, and the color of the speck corresponds to the tool, and each dot is a day. And I'm starting to look backwards in time, and each row is going to be a user, and the stacks are going to be many users. So I'm going to start looking back into our own matrix starting in 2010. And this is where people sign up. This is their first day of being on nanoHUB, and it looks pretty scattered. Can't quite see, but there's a little pattern here. There's a streak here. There's a pattern here, another pattern, little chunk, big chunks. You start to start to wonder, what is going on, right? There's people that behave similar to each other, and it looks a little bit gobbledygooky, and we wrote algorithms that categorize these people together. So you can start to look at, oh, here's a group that basically comes once and uses one particular tool and behaves the same. Here's another group that basically uses one tool, but now throughout a whole semester, this is, hold on, this is going July, yeah, so this is spring break right here. Here's another group that uses 1, 2, 3, 4, 5, 6, 7 different tools throughout a whole semester. Now, which science gateway do you know that can tell you that classes have actually utilized their site, right? We can actually quantitatively bonify the classroom size, in this case, sophomores in materials engineering, mechanical engineering, electrical engineering, freshmen in chemistry. So they have certain patterns that are indicating classroom type behavior. And then we have people that are completely uncorrelated. And I'll tell you later more how we know that these are experimentalists and how we know that these are computational researchers. And then we have a pretty big group we would call self-study users. And I'll talk a little bit more about them as well. But basically by this categorization here, we can identify in 1 year alone, we had 116 courses at 97 institutions that behaved like this. And overall, we had some 14,000 students in 760 courses and about 190 institutions that behaved like this. Now, considering that all of these are research codes that came out of research pretty recently, and since you can't do that, I think that's not quite true. Right? You can transition research codes into the classroom quantitatively. Now the question is, how long does it take for that to happen? So you can now look at these patterns and say, well, here's a tool, this particular one, purple. It came to being with a digital object identifier at a particular time, and I can measure the time between its publication on nanoHUB and its first time use in the classroom. Same for this tool, maybe here, and these other tools, right? I can measure publication date to first time in classroom. So I might want to compare that number to the typical textbook update, which is 3.8 years, according to a study. That same study says to have a new concept, you need 2 editions, right? So roughly that corresponds to 5 to 8 years, and people that have been in the business of writing textbooks, they say, yeah, that's how long it takes to write a new textbook. Now you might want to compare those years on a very different scale down to weeks on how these things show up on nanoHUB. So I'm showing you a histogram. We have some 19 tools that have been inserted in the classroom within a week of being published on nanoHUB. Some 22 within a month, some 31 within 3 months. Overall, the tools that are being used in the classroom, more than half show up faster than half a year. Right? So the median time is less than 6 months. So I would call that accelerating time to market or accelerating research into classroom in a quantitative way. All right. So now let's worry about these guys here, right? They are completely disorganized, right? Not in a nice group like that. But remember, you can't use somebody else's code to conduct research, right? It's impossible. I was told, right? So the way we measure that now and try to bust that myth is we actually look at the literature, right? People that do research publish. And when they publish, they give citations to the material they have used, right? So you look at the literature, and we can now identify some 960 publications in the scientific literature that cite nanoHUB as a resource or as a reference. And so each paper is a dot here. Color means something. I spelled it out for you here. The red ones are nano. The green ones are cyber. These are papers now on cyber infrastructure. There's now papers that discuss on how to use nanoHUB for education. And the dots are linked by lines, and the lines are common authors. So the authors are the social network between these papers. And the inside of this yellow line here, that's us. Those are people that are funded to work on this or with this. And it turns out the cool thing is that over 77% of these authors are actually on the outside. So we really enable other people to form social networks around this tool set and to use it for publication. So apparently you can do that. This myth that you have to write your own software is not quite right. And also, what we really wanted to do is reach experimentalists, not just computational geeks like me. So now we actually go also through these nano papers and decide whether or not there's experimental data in there or whether there's even an experimentalist on the co-author list. So that would indicate they're actually using nanoHUB for experimental work. And that's a pretty significant percentage. And there's even social networks that are primarily experimentalists on the perimeter. And of course, us on the inside, we always work with experimentalists all the time to validate our own tools. Right, so that's an easy one. So the myth that experimentalists will never touch this computational science stuff is busted. And without showing detailed analysis, I can say that 90% of the paper authors are affiliated with industry. So we can actually impact industry as well, just by author affiliation as well. And we're really serving a different type of customers, not just the computational geeks like me. So this is possible. But remember, this is not possible, I was told, right? So the first time I showed a social network chart like that, that question went away. You know what the next one was? Can't be good research. Not making it up, true story. So how do you measure goodness of research? I mean, typically people look at secondary citations, right? If you write a paper and it's any good or has relevance, other people will base their work on it and cite it, right? It would be a secondary citation. Now, people actually make a science out of that now where they measure how many secondary citations do I have, okay? It's called an H-index. I presume you don't know what an H-index is, so I'm going to try to explain it very easily. So if you take a person's number of papers, so this person here, faculty member 3 years after their PhD, has written about 20 papers, and one paper has been cited 60 times, the next one 40, maybe 20. In all, that person has 6 papers that have been cited more than 6 times. That person's H-index is 6, which would be considered good, because normally you'd say a person's H-index is N for N years out of grad school. Okay, that's sort of the average. So here's another person, at the time when he was elected to be Academy member of engineering, his H-index was 37. That's kind of like a lifetime achievement. Now let's step back a little bit. So he has written 37 papers that have been cited more than 37 times. One of the papers has been cited more than 1,000 times. Breakthrough paper, right? So that's a lifetime achievement and is being honored by being elected to the member of Academy of Engineering. So in 2009, we had some 575 papers, 3,200 secondary citations. Our H-index was 27 after being in business for 7 years. Today we're at 45. So not only do we allow research, apparently it's also good research according to one of these metrics. Right? So myth busted is good research. You know what the next thing is? You've got to burn a lot of CPU cycles on a computer to do real nanoscience. It can't be just toy, right? It has to be real, big, heavy compute engine tools. All right, so let me talk about those a little bit. So this is actually very close to my heart. This is Gerhard Klimeck's stuff over some 18 years of development at TI, NASA JPL, Purdue. We study quantum dots for real, so this is an indium arsenide dot and gallium arsenide surrounded by a real alloy. I have one person in the audience who will know what that is, so I'm saying that explicitly. Here's an ultra-thin body transistor, a nanowire. You might have heard of graphene, carbon nanotubes. We can simulate these devices. Those simulations can be extremely expensive computationally. So expensive that we can keep the biggest supercomputer busy in the United States. That machine has 220,000 cores. You know, one of these pizza boxes right here, 220,000 times of those, right? That machine fills this room, consumes a couple of megawatt of power, if you run, to put that in perspective, if you run for 1 hour on that machine, it would take you 25 years to run on a single CPU to solve the same problem. That puts that in perspective. It's a computation, a very hard problem. This is one of the few codes that scales that well, where you plot the number of cores versus compute time. So the ideal thing is the dashed line. In fact, this is the only engineering code that scales to this on this machine. It won a Gordon Bell Prize honorable mention. We couldn't win the full prize because the Japanese had a bigger computer that year. So that's cool. The same code base can deal with transistors that consist of basically a single phosphor atom. So we published in Science and Nature Nanotechnology, so some reputable journals. And if you invite me back, I'll talk about the single atom transistor some other time. I don't have time to talk about that today. And you know, the really cool thing is the same code base runs also in nanoHUB, powers some 8 tools, and is used by 12,000 users. Right? So the point is, to me, this is why I left JPL. Because I could not do this at NASA JPL, which is a well-reputed place. I could not put my tools into people's hands across the globe because the infrastructure didn't exist, and the scalability didn't exist, and the mechanism didn't exist. And that's why I left Southern California for all the mountains and oceans we have in Indiana. So either way, I think this is an impact that I wanted to achieve. And we have other codes. If you're in material science, you might have heard of things like Siesta, Quantum Espresso. These are all heavy-duty codes, and they've been served to over 10,000 users. So yes, a science gateway can do research, it can serve heavy-duty codes, and it can serve many, many users beyond just a single research group. So it can be computationally extensive work, and it's possible. So I'm going to wind down my presentation now on yet another myth. So, I would say 3 years ago, 4 years ago, we had a site visit. Those things are actually incredibly important, right? Every year we have an NSF site visit, they evaluate us. It's a very constructive thing, so I'm not criticizing that. But some of it is also funny. So they said, okay, you have 120 tools. Which ones are educational and which ones are research? And we give you a night to figure that out because we want the answer tomorrow morning at 8. Not making that up. So, and I felt at that time, come on, that's a wag at best, right? I mean, I can't, these are not all my tools. I don't know what the intention was of the author, right? I can look at the tool and take a wag. So, so now we actually have better ways to look at this. So now you could say, well, I know that some of these tools are used in the classroom, right? So I have a quantitative way to call something a teaching tool because they have been used in the classroom. I can devise some scale, some teaching tool index that runs from 0 to 1. And I can rank my tools according to weak usage in the classroom and heavy usage in the classroom. Forget about the formula and all that, right? But you can imagine that you have some ranking according to classroom usage. And then remember, we have these guys that are here doing it, using it in research, and we have papers that utilize these tools, right? So obviously, these tools are research tools that show up in these papers. And I can also give them a ranking from, say, 0 to 1 in terms of usage in research, right? And according to our review panel, those should be 2 orthogonal axes, and they should have nothing to do with it, because either it's a research tool or it's a teaching tool. But if you actually put it on the real scale like this, you find that tools span both. And of course, we knew that already, right? We know that SPICE came out of being a teaching tool, eventually migrated into a research and professional tool. And I didn't tell you that in the beginning, but SUPREM was a research tool, but when I was a student and learned about semiconductor processing, I used it as a teaching tool, right? For the tools we know and love, we already know we use them for teaching and for research, right? But it was inconceivable that you could have such a thing coexist, at least when we were talking to our review panel. Now, I mentioned that SPICE evolved from a teaching tool to a professional tool. And SUPREM came from a research tool used in teaching, but primarily still for research. So you start to wonder, with 12 years of worth of tool data, could you monitor the development and the evolution of these tools? As they show up on the world, in the nanoHUB world, they might show up as a research tool first. Do they migrate to be a teaching tool? Or do they show up as teaching tools and migrate into a research tool? So that's the topic of the next animation I'll show you, where we should look at basically 12 years back worth of data, and every time a tool pops into life, it pops anywhere on this chart here, and you can sort of see that in general they come from research and they trickle down into teaching. Some guys climb back up. They come from teaching and go into research. So this is actually 12 years worth of data of tool evolution, sort of highlighting that these things have a life of their own, that you can't quite predict, and you shouldn't categorize them like that. And you certainly shouldn't separate research from teaching, because those actually, at an advanced research institution, they belong together. It's our job at a research university to create the next teaching materials and the next research material, and enable them to be transitioned into the system. So that's a key element of being at a research university. Yeah. Well, we have. No. So the question is, just for the sake of repeat, the question is, how do we collect this data? We kept it all. We have 12 years worth of usage data where we know people have logged in, they have started this tool, and we looked at the correlated behavior. Have they shown up in a classroom type pattern? Then we call it a teaching tool, and we give it a teaching index. Well, if it's used for research, it shows up in a publication. So I have a qualification of how often it shows up in a research publication. And I have an index also on this axis here that indicates, well, it's been used in the classroom at so many institutions and so many classes by so many people. So we do that by usage pattern. Sorry, what? Okay. So, so let me just sort of wind this up here. So apparently we're accessible. We think we're user-friendly because people use us for publications. They use us in the classroom, in research, in education. I think with over 300 developers that participate, most of them are not being paid. We must be somewhat developer-friendly. We do that with a technology I haven't talked much about, and you can think of us as suppliers that have products. You can think of nanoHUB as a market. You can think of users as customers. And now the question is this transferable? Right? This is all nano. So in 2007, we spun what we call Hub Zero out of nanoHUB. So we created the whole infrastructure. And by today, we have some 40 hubs that are running globally in all kinds of fields of science: earthquake engineering, mechanical, cancer care, pharmaceutical pieces. Some of these hubs drive significant user numbers. nanoHUB is still the granddaddy of this, with a large user number, but overall some 800,000 visitors to these hubs. So it's a technology that is transferable into multiple hubs. So if you indulge me 2 more minutes, I'm going to try to highlight what we're going to do next, because we just won a renewal award for 10 years more funding in nanoHUB, effectively 5 plus 5. So 5 years, and then there's a renewal process. So imagine you have simulation tools used by researchers, experimentalists in education. Imagine it runs in a scientific cloud without any installation, fully operational, with built-in impact assessment. So that's a common dream. In a sense, we think we actually achieved that dream. And what we're doing now is imagining more. We believe we can extend this to experimental data You might have to do things slightly differently on some aspects. But the real goal is for you as a researcher to read your papers, say on an iPad or whatever gadget you might have, but instead of printing it out and looking at a ruler and trying to imagine what the data is that is on these graphs, you actually click on these graphs and it takes you to the tool that generated this data. And you connect back to the original data set or the original tool, and then you compare corner cases, or you compare your own tool against this data. You don't have to read it off some PDF document. You have actually access to the real data and make it reproducible. We want to do that in all areas of nanoengineering and science. We want to personalize the learning experience that people have and really become part of the day-to-day workflow. And if we are really becoming part of the day-to-day workflow, we can maybe achieve sustainability if we actually become sort of a professional society where we might have 100,000 users that actually are willing to pay $50 a year to sustain something like that, that really is part of their day-to-day workflow. So, so with that, I think I'll close up and take questions.
Thank you very much. We have 2 microphones going around. Please, if you have a question, state your name, your affiliation, and ask your question. Go ahead. This is the microphone.
Just wait.
Microphone's coming. Is it on?
Might have to turn it on. It's dead. That one is dead.
I'll give you this one. How about it?
This is a quick question. You hinted at the method you use to get a desktop app or whatever to the web. Can you briefly talk about that?
I hinted.
You hinted at suppliers or the programmers had written software that was not easy to get to the web originally. How was there a solution to that problem?
Okay.
Yeah. 'Cause yeah.
So that goes back to usually software is written for one person by one person, right? So and usually these pieces of software, I mean, they're written in C or Fortran or MATLAB, and they have an input deck that's rather cryptic and very arbitrary. We have developed a piece of software we call Rapture that allows you to describe inputs to pieces of software and outputs from pieces of software in an XML type form. So it's called Extended Markup Language. You can learn this in a couple of days, and then you can build wrappers around this science code. So you don't have to touch the science code, you just leave it as it is, and you build a wrapper around, and then a user interface is generated automatically, and it has a data management system accordingly. And over 90% of our 260 tools use this Rapture toolkit. If you have a user interface and it runs in Linux, you can deploy your code in a day. You don't have to do anything. So if it has a user interface, runs in X11 Unix, you can deploy it today. But most codes don't have a user interface, so you have to generate a simple way. And often what we do is we take in undergrads for the summer. We teach them about this Rapture. We partner them with grad students. By the end of the summer, there's a new research tool that comes out that embodies a recent piece of research. And hopefully the undergrads have learned some things about the research under the hood, and they actually have a product at the end of the summer that they can highlight that eventually has a couple of hundred users. So those are various processes we have there.
And, yeah. State your name.
Hey, I'm Gerhard DeAngelis, I guess formerly with the nanocomputing group at the University of Notre Dame. My question, I guess, is about data storage. So the work that I did involved nanomagnetic simulations using a package called OOMPH, which stood for Object-Oriented Magnetic something or other. Mm-hmm. And when you worked on a data set, or you did a simulation, the interactions that you were modeling were very complex and generated a lot of data relative to the input that you put in. And so you would end up, especially if you were doing a very high granularity simulation, with sometimes hundreds of megabytes of data per per simulation run, sometimes a gigabyte of data per simulation run. So you've got people coming to this nanoHUB tool center, I guess you could call it, running simulations, and maybe putting in an exploration space of like 100 to 1,000 different iterations on something. How are you handling the data storage? How are you handling the ownership of the data storage? And is there sort of like a long-term archiving here, or how does that work?
Yeah, so there's a whole bunch of questions right there. Right? So right now on nanoHUB, we don't have a whole lot of tools that generate that much data, or we actually end up throwing it away after the usage is done. We're getting into cataloging these data because maybe you don't want to recompute the same thing all the time, number one. Maybe you want to figure out what people have simulated already to figure out what is terra cognita, what's terra incognita, and think about what has been explored. Can you map that? So that's a piece of science by itself. Maybe you want to see how students have behaved in a class, what have they explored and what has not been explored. So there's all kinds of interesting research questions you can ask. We have a project underway which we call Instant On, which has sort of this data storage embedded in it to a certain degree, where if it has been computed, can I retrieve it, and has that author published it, or do we have to regenerate the data first in order to have true ownership of our own, right? Could they have inserted bad data into the system somehow? So there's an aspect of vetting and validation of the data that's out there. So these are not trivial things, and by no means have they been all answered. But part of the aspect is also storage. Right now is actually not that expensive, and it's getting cheaper anytime. So the question is, what's more expensive, the storing it or the recomputing it, right? Or do you maybe just store the metadata that goes along? So there's a whole bunch of questions that evolve around data, and as I had said, right, we're going to start looking at data more, and I don't think we have all the answers.
Yes, John Rumble. It's very interesting that you look at some of this from a business point of view, customers, suppliers, that kind of stuff. Who's your competition? And if you don't have any, why don't you have any competition?
It's an unfair question. Thank you.
Tough question.
So we went through a competition like this right now, right? It turned out that nobody bidded against us for the cyber infrastructure.
That just means in terms of the overall concept.
Well, it's because the incentive systems overall in academia are not in the place where serving others is being valued. What is being served, what's valued in academia is to be publishing a lot of new articles that are deemed new and generating students. To make this translational for other people and actually change what they do, you have to be pretty senior in your career to afford that, to do that in an academic environment, or crazy enough like me or our group of people that want to do that. That is not a widespread goal of people to actually change or make other people's work easier, right? With our own research, and then get our own research into their hands, right? There's tangible benefits. That's not a widespread thing, and that's why it's not a widespread approach. I think it's the best way to herd cats is to move the food. So.
Any other questions?
Hi, Carl Merrill. If I understand what you've said, most of this has been supported by the government.
Right.
And at the end, you've proposed having a society which would help support it. Am I missing something, or wouldn't that be counterproductive and then might exclude people using it? I mean, the nice thing about the government is that it sets up a commons that everybody can share, and it makes it free. But as soon as you make something a society, wouldn't that possibly restrict it?
Yeah, I agree that there will be possible negative ramifications, but maybe the society does something for the society at large as well. Like, you can go to the IEEE website, you can browse through the abstracts of papers, and then if you really want to download them for free, you either have to be part of a university or you have to be a member of IEEE to download them, or you pay them as you go, right? I mean, it's give and take, right? The NSF wants us to develop a model to be more self-sustainable. I think that's a fair way of going about it, to not be on the government dole. On the other hand, can we finance all the novel pieces from just a society aspect? I don't know. But to me, if we are in people's workflow where as we develop tools, they show up on nanoHUB automatically, it's no longer twisting arms, or as you generate data in your physical experiment, you tag later, this is publishable, this is published, this goes here. It's actually part of the normal workflow. I think we add value that might be perceived as financially valuable as well. And I think we should pursue that. We shouldn't assume that everything is given from the government. So that's my take. Ask me in 9 years when I'm like, Right. 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 Except also the Cornell guys are struggling with survival. Right? They struggle for survival. I mean, you're talking about the archives, right? So I understand. I'm part of that. I have papers on there. We use it mostly as a pre-publishing thing, right? The true vetted publication is still the one that shows up in Science or Nature or PRL, etc. Right? The archives are the pre-publication repository.
Wait.
Well, what if industry paid for nano?
What if the academia could access it for free, but industry paid? What if industry paid for the articles and academia accessed it for free?
Yeah, so then you get into all kinds of other things. Is this really something industry wants to use or should use? Then you get into IP protection. Who can see my simulations? You get into transmitting information across public channels, even if they're encrypted. The industry people I talk to, the real stuff that is close to their business line in semiconductors, they would get fired if they would put anything like that on nanoHUB. It would be a breach of IP protocol. Right? So this by itself, in this incarnation, is not really meant as an industrial resource. We can talk about creating other hubs that are now dedicated to industrial support. There's some companies that talk about building an intra-hub. There's national labs that talk about building an intra-hub inside their firewall and disseminating the tools they have this way. Right? You don't have to just have one hub. And the slides I didn't show, I've been talking about a federation of hubs that actually exchange information and all that. I mean, there's a whole lot of ways to look at making this sustainable and making it commercially viable and expanding out. Talked a lot about that.
So Larry Milstein, I'm a member of the Philosophical Society. I have a comment and a question. The first comment is that there's no free lunch. PLOS is not free. It costs money to run it, and the people who publish to it have to pay for the publication. So the last I looked, it was about $6,000 a pop for a publication. It's only free to the end user, and these are discussions about who should pay and what, how. It's not about whether it should be free or not. It's about the allocation of the costs. So it doesn't necessarily have to be a pure model where it's $50 a person and it's self-sustaining. It could be a reduced government subsidy because it's believed to be in the best interest of the public, because the public's going to get more value back than what they're putting in, plus an end user fee that recognizes the value to the end user of what they're getting. But the question is not free versus not free. The question is who pays for it, because the stuff isn't free. That's the comment. The question is, I believe you said that you're using sort of an analysis of usage patterns in order to determine what the use is. So educational uses have a periodicity tied to the semester and the breaks, and kind of the distribution of how many people are using something at one time being indicative of class as opposed to a researcher. I'm just curious, how much of the usage that you see can you actually categorize that way, and how much is kind of anomalous and you just kind of guess that it must be research because it's so aperiodic?
Yeah, so I have it in one of my slides with concrete numbers for one particular year. Let me go there. So this is taken from, I think this is academic year 09-10. So I had these categories of A, B, C, different patterns here. So we have different classes like this. So, and this is out of a subset of, I think, 8,000 users at that time. So out of those 8,000, 5,600 are behaving what we would call erratically or self-study, meaning they were not computational researchers or experimental researchers. So more than half of the users behave erratically that we cannot point to. The rest is in classrooms, or they're these experimental researchers or computational researchers. Now, what I can do for these self-study users, I can study how intensively they use the site in terms of how many CPU hours do they consume and how many runs do they do. And what the users we call self-study users actually, in terms of intensity of their use, behave like classroom users. And that's 2 orders of magnitude lower in number of runs and CPU time consumed compared to these researchers. So in terms of their requirements or the actual usage, they behave like classroom users, even though they don't have a user-user correlation. Okay? Does that make sense?
I think you're saying 50% are erratic, but they look like they're educated.
Right. Or they're formalized. That's right. That's right.
Any other questions? Oh, one more, okay.
Gerhard DeAngelis again, University of Notre Dame. Just a really quick, I guess, observation. You talked earlier about how some of the other tools like SPICE and other stuff in that vein have kind of been adopted by industry because they were first adopted by educational institutions. And of course, well, it sounded like that. Am I not quite right? Like
Well,
the
what I
people.
meant to say is, as those tools have been developed at universities, with the people that were involved, they either migrated along to industry or they migrated into academia. They were taken along by personal ventures, personal history.
Sure. I would suggest, and it sounded like you would suggest, that the same mechanic might be at work here if this is obviously catching on, and the same mechanic might be at work here. So you could have the same, really also all a project needs like a project like this needs is uptake, right? Is people to want to use it. So if you have that happening in academia and you have that happening in communities of undergrads, communities of graduate students, those same people are going to take it on to academia and are going to take it on to, they're going to tell their superiors in industry, hey, we really need something like this. Can we, fork our own, on GitHub or something.
Mm-hmm.
And so I think this ease of commercialization, I think, is probably not going to be too much of a barrier, probably because of that mechanic.
I hope so. I hope you're right. I mean, we have some concrete cases of evidences where this is happening, right? But it's not, I'm still not driving a Porsche, okay?
Any other questions? I guess that's it. Thank you very much. We have the announcement framed and signed by the members of the General Committee for you to keep.
Thank you.
Oh.
Okay, thank you. Oh, yeah. Larry reminded me there's some flyers out there on myth busting and nanoHUB. If you're interested, they're laying at the table. Feel free, then I don't have to carry them back home. If you're not interested, that's fine too. I'll take them back home.
Thank you very much again.
Thank you.